Picture a cup falling off your table and shattering into pieces. Now imagine watching that scene in reverse. All those scattered fragments jumping back together, forming a perfect cup that leaps onto the table. Something feels deeply wrong about that reversed video, doesn't it? But here's the thing that keeps physicists up at night. The fundamental laws governing every atom in that cup work just fine in both directions. They don't actually care whether time flows forward or backward. So why does the cup never reassemble itself? Why do we remember yesterday, but not tomorrow? This is one of the biggest mysteries in physics, and it has to do with something called entropy, basically the measure of disorder in a system. Back in 1927, British astrophysicist Arthur Eddington gave this puzzle a name, the arrow of time. He was trying to capture this weird one-way quality that makes time fundamentally different from space. In space, you can move left or right, up or down, forward or backward. No problem. But time? You're stuck moving in one direction, whether you like it or not. The answer lies in the second law of thermodynamics, which says that entropy in an isolated system tends to increase over time. Think of it like this. There's only one way for your room to be perfectly clean, but millions of ways for it to be messy. Since the molecules and objects in your room are constantly jiggling around, thanks to thermal energy, they're much more likely to end up in one of those many messy arrangements than the single clean one. This principle explains pretty much everything we see around us. Your coffee gets cold because there are vastly more ways for heat energy to be spread out between your coffee and the room than concentrated in just the coffee. Ice melts in your drink for the same reason. And yes, cups break, but don't unbreak, because there are countless ways for the pieces to be scattered, but only one way for them to form a perfect cup. I remember sitting in a physics lecture years ago when this really clicked for me. Actually, wait, I was stirring cream in my coffee, watching those beautiful spiral patterns form, and it hit me that I'd never once seen the cream spontaneously separate back out. Not once. And neither have you. The weird part is that at the microscopic level, physics is mostly time-symmetric. The equations describing how particles interact, how forces work, how energy flows, they run just fine backward. It's like having a recipe that works whether you read it top to bottom or bottom to top. Yet somehow, when you zoom out to everyday objects, this symmetry completely breaks down. In the 1870s, physicist Ludwig Boltzmann thought he'd figured it all out. He showed mathematically how molecular collisions in a gas would naturally lead to increasing entropy. Problem solved, right? Well, his colleague Johann Loschmidt pointed out a devastating problem. If the laws of physics are reversible, then for every process that increases entropy, there should be an equally valid reverse process that decreases it. Just reverse all the velocities of all the particles, and your mixed-up gas should unmix itself. This is Loschmidt's paradox, and it's a real brainbender. The resolution comes down to probability. Yes, entropy can decrease. It's physically possible. But the odds are so astronomically small that it might as well be impossible. Imagine flipping a coin 1,000,000,000,000 times and getting heads every single time. Technically possible? Sure. Going to happen? Not in this universe. Actually, let me correct that. Modern experiments with quantum systems have shown that at very small scales, for very short times, entropy can indeed decrease. Scientists have even created time-reversed states in quantum computers. But these are tiny systems for tiny fractions of a second. Scale up to anything approaching everyday size, and the second law reasserts itself immediately. The numbers involved here are mind-boggling. Take a typical glass of water. It contains something like 10 to 25 molecules. That's a 1 followed by 25 zeros. For all those molecules to spontaneously organize themselves in a way that decreases entropy significantly, The odds are so small that you'd need to wait many times the current age of the universe to have even a tiny chance of seeing it happen. But here's where things get even stranger. Quantum mechanics adds a whole new layer of weirdness to the arrow of time. In a quantum world, particles exist in what's called superposition. They can be in multiple states simultaneously until they're observed. When you measure a quantum particle, this superposition collapses into a definite state. And this collapse? It appears to be irreversible. You can't uncollapse a wave function. Once you've measured a particle's position, you can't unmeasure it and return it to its original superposition. This gives us what some physicists call the quantum arrow of time. Though whether this is fundamentally the same as the thermodynamic arrow is still hotly debated. Recent research by teams at the University of Surrey has shown something fascinating. Quantum systems can theoretically experience time flowing backward just as easily as forward. The equations don't care. It's only when these quantum systems interact with their environment, when they become entangled with a larger world, that a preferred direction of time emerges. This process, called decoherence, might be the bridge between the reversible quantum world and our irreversible everyday experience. When a quantum system interacts with its environment, information about its state spreads out into that environment. And just like with the broken cup, gathering all that dispersed information back together is practically impossible. The connection between entropy and information turns out to be crucial. Every time information is erased, entropy must increase somewhere. This is called Landauer's principle, and it sets a fundamental limit on how efficient computers can be. Every deleted file, every cleared memory register, every forgotten thought increases the universe's total entropy by at least a tiny amount. Think about what this means for memory itself. A memory, whether in your brain or on a hard drive, is a physical pattern that correlates with something that happened earlier. Creating that pattern requires energy and increases entropy. This is why we can remember the past, but not the future. Forming memories of the past increases entropy in the right direction, but forming memories of the future would require entropy to decrease, which basically never happens. Leonard Mlodinow and Todd Brun discovered something remarkable about this connection. They proved that any system capable of remembering the past must necessarily experience time in the same direction as increasing entropy. It's not just that our psychology makes us perceive time this way. The physical nature of memory requires alignment with the thermodynamic arrow of time. This connection between memory and entropy explains something we all take for granted. Why can you remember what you had for breakfast yesterday, but not what you'll have tomorrow? It's not just a quirk of consciousness. It's baked into the fundamental physics of information storage. Any system that stores information about another system must do so in a way that increases entropy, and this automatically creates a directional relationship with time. Think about a simple turnstile counting gas molecules passing between two chambers. The counter creates a memory of past molecular traffic. But here's the key insight. This memory is only reliable for recording the past, not predicting the future. Small changes in molecular positions now won't affect what the counter already recorded, but they could completely change what it will record later. Memory is inherently backward-looking because of how information and entropy work together. Now let's zoom out to the cosmic scale. If entropy always increases, the universe must have started in a state of incredibly low entropy. And according to the Big Bang Theory, it did. The early universe was hot, dense, and remarkably smooth, a very special, very low entropy configuration when you factor in gravity. Wait, that sounds backward, doesn't it? Hot and smooth sounds disordered, not ordered. Here's the counterintuitive part. For a system where gravity matters, clumpy is actually higher entropy than smooth. A universe with all matter collapsed into black holes has much higher entropy than one with matter spread out evenly. So our universe started in an incredibly special, low entropy state and has been evolving toward higher entropy ever since. Roger Penrose calculated just how special this initial state was. The odds of randomly selecting a universe with entropy as low as ours at the Big Bang? About 1 in 10-10-123. That number is so incomprehensibly large that if you try to write it out in full, using every particle in the observable universe to write one digit, you'd run out of particles before you ran out of zeros. This raises a profound question. Why did the universe start with such low entropy? Physicist David Albert calls this the past hypothesis, the assumption that the universe began in a very special, low-entropy state. Without this initial condition, the second law of thermodynamics wouldn't work, and we wouldn't see an arrow of time at all. Some physicists find this deeply unsatisfying. It feels like cheating to just assume the universe started in a special state without explaining why. Various theories have been proposed. Maybe our Big Bang was just one of many in a larger multiverse. Maybe time itself is emergent and the question is meaningless. Or maybe the universe's initial state was somehow natural or inevitable given some deeper principle we don't yet understand. The cosmic expansion adds another wrinkle to the story. As a universe expands, it creates more space for entropy to increase. Galaxies form, stars ignite, planets coalesce, each step increasing the universe's total entropy. We're still riding this wave of entropy increased billions of years later. The universe is heading toward what physicists rather dramatically call heat death, a state of maximum entropy where nothing interesting can happen anymore because there are no energy gradients left to drive any processes. But don't worry, we got about 10 to 100 years before that becomes a problem. Plenty of time to figure something out. Speaking of time, here's something that might blow your mind. Physicists have actually found violations of time symmetry at the fundamental level. Remember how I said the basic laws of physics don't care about time's direction? Well, that's mostly true, but not entirely. In 2012, researchers at the Bobber experiment at Stanford made a groundbreaking discovery. They were studying particles called bemesons, exotic particles that only exist for tiny fractions of a second. These particles can oscillate between matter and antimatter states. And the team found that this oscillation process is not the same going forward in time as backward. This was huge. For the first time, scientists had directly observed time asymmetry in fundamental particle physics. The statistical significance was extraordinary, what physicists call 14 sigma, meaning the odds of it being a fluke are basically zero. The laws of physics, at least in this one corner, actually do distinguish between past and future. But even this fundamental time asymmetry isn't enough to explain the dramatic arrow of time we see in everyday life. The violation is subtle, rare, and only happens in exotic particle interactions. Your coffee doesn't get cold because of meson oscillations. Andrea Rocco from the University of Surrey puts it well. When you watch a process like spilled milk spreading across a table, it's clear that time is moving forward. But if you played it backward, like a film, you'd immediately realize something's wrong. The puzzle is that at the most fundamental level, the laws of physics look like that reversible film. They work just fine running backward. So we have multiple arrows of time: thermodynamic, cosmological, quantum, psychological. And while they all seem to point in the same direction, physicists are still working out exactly how they're connected. It's like having several clocks that all tick forward, but being unsure if they're running off the same mechanism or just synchronized by coincidence. One fascinating possibility is that all these arrows are different faces of a single, deeper principle we haven't discovered yet. Maybe entropy, quantum decoherence, cosmic expansion, and memory formation are all aspects of some more fundamental feature of reality. Some physicists think this might be related to quantum gravity, the still undiscovered theory that would unite quantum mechanics with general relativity. The role of observation and measurement adds another layer to the puzzle. In quantum mechanics, the act of measurement seems to pick out a special direction in time. Before measurement, a quantum system evolves smoothly and reversibly according to the Schrödinger equation. But measurement causes an irreversible collapse. This has led some physicists to suggest that consciousness or observation might play a fundamental role in creating time's arrow. I should mention that this idea is highly controversial. Most physicists think the arrow of time must have an objective, physical basis that doesn't depend on observers. After all, entropy was increasing for billions of years before any conscious beings evolved to notice it. The universe doesn't need us to tell it which way time should flow. But the connection between information, entropy, and observation remains profound. Every measurement, every observation, every bit of information gained about a system increases the total entropy of the universe. In a very real sense, learning about the world is a thermodynamic process that contributes to time's arrow. Life itself is intimately connected to the arrow of time. Every living thing maintains its internal order by increasing entropy elsewhere. We eat food, burn fuel, radiate heat, all processes that increase the universe's total entropy while allowing us to maintain our complex structures. Without the arrow of time, without entropy increase, life as we know it couldn't exist. Think about photosynthesis. Plants capture low-entropy sunlight and use it to build complex molecules, seemingly decreasing entropy. But the overall process, including all the heat radiated away, increases total entropy. Life doesn't violate the second law. It surfs on it, using energy gradients to maintain and replicate complex structures. The implications of this go even deeper when you consider evolution. Natural selection requires reproduction with variation, and reproduction is fundamentally a process of creating copies, adding information to the universe. Every time DNA replicates, every time a cell divides, entropy increases somewhere. Evolution itself is a temporal process that only makes sense with a clear arrow of time. You can't evolve backward any more than you can unbreak an egg. Actually, that egg analogy is perfect here. When you crack an egg to make an omelet, you're dramatically increasing entropy. The highly ordered structure of the egg, with its separate yolk, white, and shell, gets scrambled into a disordered mixture. No amount of stirring will unscramble it. The information needed to reconstruct the original egg structure has been irretrievably dispersed into thermal motion of the molecules. This brings us to a profound realization. The arrow of time isn't just something that happens in the universe. It's woven into the very fabric of causality. Causes precede effects because of the thermodynamic arrow of time. We can influence the future, but not the past, because influencing something requires energy transfer, and energy transfer increases entropy in a forward time direction. Some researchers have even explored whether the arrow of time might someday reverse. If the universe stops expanding and starts contracting, the big crunch scenario, would entropy start decreasing? Would time run backward? Most physicists think not. Even in a contracting universe, local processes would likely still increase entropy. But honestly, We don't know for sure. The universe has surprised us before. Thomas Gold once proposed the most radical idea that in a contracting universe, the arrow of time would reverse, and conscious beings would still perceive time as flowing forward from their perspective, from low to high entropy, even though from our current perspective they'd be living backward. Their future would be our past. It's a mind-bending idea that's probably wrong, but impossible to definitively rule out. Let me tell you about something even weirder. Some physicists have suggested that the arrow of time might be different in different parts of the universe. Maybe there are regions where entropy is decreasing, where time effectively runs backward from our perspective. The inhabitants of such regions, if they could exist, would perceive their time as running forward and ours as running backward. We'd be living in each other's past. However, most evidence suggests the arrow of time is universal, at least in our observable universe. We see the same direction of time in distant galaxies as we experience here on Earth. Light from billions of years ago shows stars forming from gas clouds, entropy increasing, not the reverse. The cosmic microwave background radiation shows the universe was once in a lower entropy state everywhere we can observe. The development of complexity in the universe follows a predictable pattern tied to entropy increase. First, gravity caused matter to clump into stars. Stars fuse hydrogen into heavier elements, increasing entropy through nuclear processes. When massive stars exploded as supernovas, they scattered these heavy elements through space, enabling the formation of rocky planets. On at least one of those planets, complex chemistry led to life, which has been creating increasingly complex structures while increasing universal entropy for billions of years. Each step in this cosmic evolution was only possible because of the arrow of time. Stars can only shine because they can radiate heat into cold space. Planets can only form because angular momentum can be dissipated through collisions. Life can only exist because it can dump waste heat into its environment. The arrow of time also explains why certain processes in nature are irreversible even though the underlying physics is reversible. Take friction, for example. When you slide a book across a table, kinetic energy gets converted to heat through friction. The organized motion of the book becomes disorganized thermal motion of molecules. While it's theoretically possible for all those heated molecules to spawn, never happens. Or consider mixing. When you add milk to coffee, the two liquids mix through diffusion and turbulence. Unmixing them would require precisely reversing the motion of trillions upon trillions of molecules. The information needed to accomplish this reversal has been dispersed into molecular motions that are practically impossible to track and control. I just realized I've been talking about information a lot without really explaining why it's so central to understanding time. Here's the thing. Information and entropy are intimately related. In fact, they're essentially the same thing viewed from different angles. Entropy is missing information. Information you'd need to completely specify a system's microscopic state, given only its macroscopic properties. When a system's entropy increases, you're losing information about its detailed, microscopic configuration. That lost information doesn't disappear. It gets spread out into correlations with the environment that are too complex to track. This is why the arrow of time is sometimes called the arrow of increasing correlations. As time moves forward, different parts of the universe become more correlated with each other in increasingly complex ways. The computational perspective on the arrow of time is fascinating. Every irreversible process can be thought of as a computation that destroys information about its inputs. When your computer deletes a file, it's increasing entropy. The information in that file doesn't vanish. it gets converted to heat that radiates away from your computer circuits. This heat carries the information away in a form that's practically impossible to recover. This has led some physicists and computer scientists to suggest that the universe itself might be computational in nature. Maybe reality is fundamentally about information processing, and the arrow of time emerges from the computational irreversibility of certain operations. It's a radical idea that's hard to prove or disprove, but it offers a different angle on why time has a direction. The philosophical implications are staggering. If the arrow of time is just a statistical tendency rather than a fundamental law, what does that mean for free will? For personal identity? For the nature of causation itself? These questions have kept philosophers busy for decades and show no signs of being resolved soon. Some philosophers argue that without a fundamental arrow of time, our entire conception of reality breaks down. How can anything cause anything else if time doesn't have a real direction? Others argue that the statistical arrow is enough, that overwhelming probabilities are just as good as certainties for practical purposes. There's also the question of whether time itself is fundamental or emergent. Maybe time, like temperature, only makes sense for large collections of particles. Maybe at the deepest level of reality, there is no time, just patterns of correlation that give rise to the appearance of temporal flow at larger scales. Recent work in quantum gravity suggests this might be the case. In some approaches to quantum gravity, time disappears from the fundamental equations. It only reappears when you look at the aggregate behavior of many quantum gravitational degrees of freedom. If this is right, then asking why time flows forward might be like asking why heat flows from hot to cold. It's just what happens when you have lots of particles behaving statistically. But even if time is emergent, that doesn't make it less real. Temperature is emergent from molecular motion, but it's still real enough to burn your hand on a hot stove. The arrow of time might emerge from more fundamental physics, but it still shapes everything about our experience of reality. As we push the boundaries of physics, new questions about time keep arising. What happens to the arrow of time near black holes, where space-time itself gets twisted beyond recognition? Does time have a direction in the quantum foam at the Planck scale? Could advanced civilizations ever harness energy from entropy gradients to reverse local arrows of time? These aren't just academic questions. As we develop quantum computers, explore space, and push the limits of technology, understanding the arrow of time becomes increasingly practical. Quantum computers already exploit quantum superposition to perform calculations impossible for classical computers. Who knows what other technological miracles might be possible once we fully understand time's arrow? The arrow of time remains one of the deepest mysteries in science, connecting thermodynamics, cosmology, quantum mechanics, and consciousness in ways we're only beginning to understand. Every answer we find seems to raise new questions, pushing us deeper into the fundamental nature of reality. So the next time you see a glass break, remember, you're witnessing one of the universe's most profound mysteries in action. That simple, everyday event embodies questions that have puzzled the greatest minds in physics for over a century. The arrow of time isn't just about why things break. It's about why anything happens at all, why we exist, and why the universe is the way it is. And that broken glass? It's definitely not coming back together. The universe has already moved on, carrying us all inexorably into the future, one increasing bit of entropy at a time.